So we talk about the quantum chemistry. One of the goals of quantum chemistry is to allow practicing chemists to use knowledge of the electronic states of fragments, such as atoms, radicals, ions, molecules, to predict and understand the behavior. For example, electronic energy levels, geometries, reactivities of larger molecules. We must first write down n electron wave functions that possess the appropriate symmetry. This task requires combining symmetries of the occupied orbitals to obtain the symmetries of the resulting states. Electrons are placed into orbitals to form configurations, each of which can be labeled by its symmetry. The configuration may interact strongly if they have similar energies. So electrons' location in a specific orbital is important to know to understand the correlation between two electrons in atomic orbitals of the same symmetry to form molecular orbitals in simple or higher molecules. So the quantum theory could prescribe those interactions along with the wave functions of electrons. So my understanding is the other theories didn't give us the exact location of electrons. Just when says the d electrons are like 3 electrons in d, and you can put them in T2G. So we started to put them in like dxz, dyz, dxy. So why we don't move it around, or how can we be certain that this electron will sit or occupy this orbital? So there is no specific rule is being given to put the electron. Only it says by Horn's rule or against Horn's rule, distribute singly in orbitals. So once we have 3 similar orbitals, 3 similar level energy orbitals, how can I put it like from the left singly or from? So there is no obligation to, or certain rule to put this electron exactly in this orbital. So that's why, and then the electron have a wave function. So the wave function of electron, it didn't been described in the orbital, or how the electron is moving, like clockwise, spinning clockwise, anti-clockwise. It just says, just put the electron in the orbital singly and then couple them. So which orbital in which electron in which orbital should be put, and the how they correlate, how they interact together in the orbital. How can you force them? So there is no certain rule in previous theories, atomic molecular atomic theory or molecular theory or crystal field theory, ligand field theory. All of them, they didn't focus on specifically on the behavior of the electron, which is very important in the orbital. So it was when being described, it's in bulk. It wasn't specific. So how can you the ligand field theory the first time introduced the word symmetry, or previously with the crystal field there was orbitals symmetric to each other, so they will interact, but more being focused in the ligand field theory that these atomic orbitals should be interact in the same symmetry, in the same, they can come from different energy level and occupy same energy level by combination. So the sometimes says there is, okay, ending with 4s2 3d1 and the carbon like 1s2 2s2 2p2. So it says, yeah, there is a hybridization or excited state. Either the carbon on its own, so the distribution of electrons will be 2 electrons in S, 2 electrons in P. But if being reacted with another atom, it says, yeah, sometimes the lone pair in the 2s will remain as they are, non-bonding, or sometimes one of the electron will jump or promote it to another orbital in the P. So it will become from 2s2, 2p2 to become 2s1, 2p3. Who will rule such promotion? So that's been not been discussed in details. So that's why the quantum number or the quantum theory was very important to talk about behavior of every single electron, where you can find it, where it's localized or where it's being found in which orbital. And every electron has 4 quantum numbers. And these 4 is the ID of each electron. And no 2 electrons share the similar 4 quantum numbers, never. And this is very precise. And then from there, we can describe the electron itself in its specific orbital. So ligand field spectra introduce Russell Saunders term symbols and term states. Term symbol, term states. So if you consider 2 electrons system, for example, a D2 ion, the interactions that can occur are of 3 types. These are trends in the coupling as, so we have 2 electrons in the D2, they can be coupled. There will be spin-spin coupling, orbital-orbital coupling, and spin-orbit coupling. So now, for the first time, we hear about the spinning between these 2 electrons, spin-spin, okay, or without electron, orbital-orbital coupling, or there is an electron inside the orbital and they will couple. So spin-spin coupling is termed by S capital. The resulting spin quantum number of a system of electrons is denoted by the capital letter S. It is obtained by coupling the spin quantum numbers for the separate electrons, and according to the there is S, you have 2 electrons, everyone has a spin, so there is spin 1 plus a spin 2, or there is spin 1 plus a spin 2 minus 1, and so on. So there is a these 2 brackets, they have to come out with positive charge of S1 minus S2, always positive. Angular momentum, the inner quantum number, and spin orbit coupling. So the value of J, this is the first time we talk about a J value, which determines the shape of an orbital and amount of angular momentum associated with an electron in it. So orbital angular momentum, there is orbital angular momentum equals to, in brackets under the square root L times L plus 1 closed times H over 2 pi. This is along z-axis only. So there is a direction of this orbital angular momentum. So we have a direction. Which direction is taking this angular momentum? So that's J is determine the shape of the orbital. Electron rotates along the axis, pass through the nucleus, then generates magnetic moment. So electron in S, you know, orbital S is L. So the name of the S is L orbital, describe orbital, which is equals to 0. When there is L equals 0, this is orbital S. So this orbit has no orbital angular momentum. Why? So because of the S is spherical, so there is no direction, no such a direction for the ball. Wherever you put it, it's like a same direction. So only S, L is 0, so there is no orbital angular momentum. But in P, when L is 1, so this will take under, if you put, okay, let me have a look here. So if you L, when L is 0 here, so 0 times 0 plus 1, what will be? It will be 0. So everything is 0 here, is gone. But if you put, replace L by 1 here, so 1 times 1 plus 1 will be under the square root 2 times H divided by 2 pi. So the Z component will have degenerate value. So here we have the ML being, this is the, sorry, this is belong to which? This is belong to D. So the plus 2 times plus 2 plus 1, 0, minus 1, minus 2. Here, if you have a D, so an electron, sorry, I need to put these, copy. Yeah. So this belong to D, and sorry for that. And here you can see is, so, and the Z component will have, if you take the Z, so will degenerate. So I will remove all of this and take this value here to be copied. And I will put them here. Yeah. So now what I have here is the electron, an electron in orbital d, L equals to 2, has the angular momentum of, so if you put 2 instead of L in this, it will be 2 times 2 plus 1 will be 3. 2 times 3 will be 6 under the square root divided, multiply by h over 2 pi. So if an atom placed in a magnetic field, the degenerates will be removed. So now you can see here the ML being degenerated, 2 plus 2 plus 1, 0 minus 1 minus 2. So we have 5 degeneracy. 1, 2, 3, 4, 5. So electrons in various d orbital will interact with that magnetic field to some extent or of their orbital angular momentum. Electron has a spin, angular momentum from rotation about its own axis. So the magnitude is called spin angular momentum. So now we are introducing the new term. So before that, we had the orbital angular momentum. For the L equal to 0 will be S. For L, so there is no angular moment, orbital angular, but in P, we have P equals to 1, and then we have to put it in the equation, and we can end up with in this equation, it will end up with what? With 2. So under the square root. If you put 1 instead of the L, you will end up with 2 under the square root. That's for the P. And for the D orbital, you will end up with under square root 6. And here you have 5 degenerate suborbitals. And then every electron has a spin angular momentum, and that is like S plus 1 under the square root multiplied by h over 2 pi. So it's similar to L. You put L instead. So the S, I think here the S should be in capital letter. So now S is the spin. So any electron has a spin angular momentum. It can form in this equation. So the Z axis direction, where S is spin, quantum number, ms is the direction of the spin, can be plus half or minus half. So clockwise, anti-clockwise. These will give Z component values of plus half, minus half. Okay. So if you put half here, half times half plus 1 will be 1.5 times half will be, and then you can see the values coming from the S spin angular momentum. So for the J, which describe the direction, as we say the direction, is the inner quantum number. Take this value, and we need to know that J equals to L plus S or L minus S. So why you see the bracket here is like this, and here you have it, because every time you end up with positive charge. So the value must be positive. So if L equals to 0, it is S orbital. So electron has no angular momentum. J will equal to S. Okay. So J will be equal to S when there is L is 0. So the Z component of the total angular momentum is J times H over 2 pi. And there are 2J plus 1 possible orientation in space. And for electron in, I don't know how many S orbitals, so L is 0. J can only be half when this direction electron being promoted. So the Z here equals to J. So the total angular momentum is Z. Total angular momentum. Spin. So in all cases, when you write here orbital angular momentum along Z-axis, so this is Z. Okay, so every time you have to write Z, and to see that what is this, Z is the orbital angular momentum or spin angular momentum or the direction. So spin angular momentum is Z here as well. You can count it, and it will be like this. Under the square root is S plus 1 or times H over 2 pi. With the application, when we do the theoretical calculation, you will find out it's easier to understand. So as we said, the J angular momentum Z, again, is along the Z axis. So you have it on the direction of the orbital. So there is a spin orbit coupling here. This is the spinning of the electron, and this is the orbital spinning. So there will be interaction between them. So this is for a free atom and ions, Russell-Saunders coupling. In atomic spectroscopy, this coupling also known as ALS coupling, because it is orbital spin coupling. Specific coupling scheme of electronic orbital angular momentum. Orbital momentum and the spin angular momentum. I don't want to leave anything beside it, just to stay as it is. So there is a orbital angular momentum because of the spinning, and there is a spin angular momentum of the electron. So the coupling scheme is named after H.N. Russell and Saunders, 1925. This is mainly for the lighter atoms or atomic number less than 57. This is very suitable for such atoms atomic number less than 57. The four quantum numbers: principal, you know, orbital, principal is N, orbital L, magnetic is ML, and spin is MS. So every one of them, you can see S when there is 0 L. When the L is 1, it's a P. When L is 2, is a D. L is 3, is a F orbital. And every one of them is degenerating position, whether +1 to the left, -1 to the right, must be. So the S has only one room. ML is 0. S, when L is 0, ML is 0. And it's orbital S. When there is P degenerate, +1, 0, -1. So these will show you exactly the position of the p orbital. And +1 is to the left, 0 in the middle. If the electron found in the -1, it means to the right. And then you have ML. These are the values of ML. So ML, is it +1 or 0 or -1? So P equals to L is what? 1. If L is 0, it means S. L is 1 is P. L is 2 is D. And D is 5 suborbitals. So you start with +2, +1, 0, -1, -2. If the F, you have 7 suborbitals, starting with +3, in the middle 0, to the right is -3. So now we have these and we can apply the 4 quantum number. Don't forget the orbital angular momentum, Z, is what is L +1 under the square root times H divided by 2 pi. The net, okay, so that's in small letter. If you have a net orbital momentum, it will be in capital letter. The net orbital angular momentum, so the total of them will take the L capital letter +1 multiply by this. So since the value of ML for any electron denotes the component of its orbital angular momentum along z-axis, ML is this one. Algebraic sum, individual electrons give orbital magnetic quantum number is ML. That's for the total. In Russell-Saunders coupling, the orbital angular momentum states electrons. So you have the total here of L, always positive. So you have the value here. You don't need to memorize this. It's always L square is positive. Total angular momentum is coming like in this. So one electron spin functions are coupled to the state with a quantum number S. Total spin angular momentum squared, S to the power 2. If there is SS, so it will be S to the power 2. To describe electron state in the atom, the term symbol usually follows the electron configuration. So first you have to introduce electron configuration to find the last electron. So there is JJ coupling as well. J is what? Capital letter is L capital plus S, or J equals to L minus S, but always coming out in positive charge. So it should be integer. When you put L plus S comes out positive. When you put integer, whatever value you come out here should be changed to positive, which is more used for atomic number more than 57. This J capital more than 57, but the small j is the coupling between the orbital and the spin of the electron. So more than the small letter j prescribe the coupling between electron and orbital less than atomic number of 57, but J capital will go higher. So now term symbol, we can see the terms. If ML small letter orbital will be S, P, D, F, G, H, I, K. So here the term for S, L is what? 0. For P, 1. D, 2, and so on. The L term, L orbital term will be capital letter. You have to use capital S when you count the total spinning. So the Russell-Saunders term symbol result from these consideration is given by superscript 2s plus 1. And total orbital angular momentum as you put it here. So now you are prescribing the L is the total, which is the orbital, which orbital is it? Is it S? You put it instead of the L. Is it P? Is it D or F? You replace the L. But when you count 2s plus 1, you go with the spin. What is the status of the spin? Is it half, minus half? You put it the top left. To the lower right, it will be J. And the J here is what? The coupling between S and L. So if J value omitted, ignored the ground term symbol. So sometimes we say, what is the ground term symbol? So you ignore the J. Okay, you only put this equation and count which number will be at the top here. Okay, so now we go to application. The combination of spin S value and orbital L is called a single ground term symbol. So L is 2s plus 1. So when you have S, it means one orbital, which is S. When you have, there is a one electron here, or you have two electrons in S. This is maximum. So ML is 0. ML is 0. Combination of S and L called a level J is inner quantum number. So you can go with J. And J is coming from the combination of, I will show you, you have to calculate J in terms of L plus S, and J is the integer of L minus S. L plus S when the orbital more than half filled. This is important. Orbital is half filled. So you apply L plus S, more than. If it is less than half filled, you use L minus S. So now here is half filled. So the L is equal to S, or J equal to one of them when it is half filled. This is half filled. So here J is equal to S or equals to L. When you have more than half filled, you have to add value of S to the L to get the J. And if you have less than half filled, you go with minus, but integer. So J equals to S because L is 0 for orbital when filled or half filled. So if you count ML, if this is, so you add +1 to 0 to -1. What do you end off? What is the result? What did we say? L capital is the result of adding all ML's values. The L capital. S capital is adding all single electrons. Half plus half plus half. So if you have ML is +1, 0, -1. So the total L will be +1, +0, -1. In total will be 0. So L is 0. What does it mean when L is 0? The remaining will be J equals to S. When L equals 0, and here is half filled, it means ML is 0. So how many MLs in total you have? I have only one, only 0. So when total of ML is 0, which is half filled, it means you omit the L value, and you end up with J equals to S. That's it. So how many? S here is half, so J will be half. S here is half and half and half, 3/2, or 1.5. So that should be 3/2. Must be 3/2. You don't do fraction. You do fraction. You don't do a normal number or digital decimal number. So it should be 3/2. So here we have the total number of L from ML S. The total number of ML is 0. The total number of S is half and half and half. It will be 3/2. So now J equals to S. And you can do the possible number of microstates associated with this level. You can correspond to the term 2S plus 1 times 2L plus 1. This is, at the end, you can count the microstates value. So a combination of L, S, J, and MJ determines the level of a single state. Terms has a statistic weight of 2J plus 1, and you can put it here. So this is the final law of the term symbol. You can find the L. What is it? Is it S, P, D, F? To the top left, you multiply 2 times how many spins you have, how many halves, plus 1. To the lower, you can count 2J plus 1. What is the J? Depend on these. And then you multiply 2J plus 1, you end up with number here, number here. So this, they call it the possible electron orientation in space. Summary. So 3 term symbols must be calculated for a free element or ion. So now we are talking about free elements. So the first one is the ground term symbol. 2S plus 1 L. Or the level term symbol 2S plus 1 LJ. What do you have J value? L plus 1 when it is more than half filled. J equals to L minus S integer will be less than half cell. But if you have J equals to S when there is L equals to 0, total, when filled or half filled, you always end up with L equals to 0. So state term symbol is what? State. 2S plus 1, L, 2J plus 1. Number of microstates, you multiply 2S plus 1 times 2L plus 1. We have application and talk about it later.